So in case 3, we're going to be looking at a new case for us where we have one eigenvalue is 0 and one is non-zero. I just want to point out that in terms of the matrix of coefficients A, this is the first case we're looking at where the determinant of the matrix will be actually equal to 0, as can be checked for these types of examples. In case 1 and case 2, where we had distinct non-zero or complex eigenvalues, the determinant of the matrix was not 0. Alright, this is going to lead us to more than one equilibrium solution, so the origin won't be the only equilibrium solution, as we're going to find out. Now, you still can build up the same kind of general solution. So you're still going to write down K1 times e to the lambda 1t times V1 plus K2 e to the lambda 2t times your eigenvector V2. Now the only difference is for this one is because e to the 0 is 1, because one of our eigenvalues is 0, this term gets, this factor I should say, is just 1. Alright, so what that ends up leading to is we're going to get in this type of situation a whole line of equilibrium solutions. Alright, in fact, if we let K2, the constant K2, be 0, and K1 be any real number, then that will be a solution. And therefore, well, what's K1 times the fixed vector V1 if that's its corresponding eigenvector? Again, V1 and V2 are eigenvectors corresponding to lambda 1 and lambda 2. They're constant vectors. K1 times a constant vector is just a fixed vector or a fixed point. So it's a single point, meaning it's a equilibrium solution. It's a constant solution. All right, and they're thinking about the long run behavior. It's a little bit simpler in this case. It's only going to depend on lambda 2 because the e to the lambda 1t part is just 1, so that has no effect as t goes to infinity. That part's constant, so it's either going to go to infinity, all right, if lambda 2 is positive, or go to or approach k1 times v1 if lambda 2 is negative. Okay. Again, lambda 2 we're assuming is non-zero. It's either positive or negative, not 0. We'll handle the repeated case in case 3. All right, so again, thinking about the solution, this part right here is either going to go to 0 or this is going to go to infinity, the e to the lambda 2t part, as t approaches infinity. It'll go to 0 if lambda 2 is negative. It'll go to infinity if lambda 2 is positive. So that describes the end behavior. Now let's move on to an example with this. So this is be kind of our first example. We probably could have rolled this into case 1 because the solution is developed in the same, a very similar way, where you have two different eigenvalues and you find their corresponding eigenvectors, V1 and V2. The only difference between case 1 and case 3 here is that in case 1, the determinant of the matrix was non-zero. The only equilibrium solution we had was the origin. In case 3, we are going to see we will have other equilibrium solutions besides the origin. So in this example, we've got the coefficient or the coordinate component format, on the left, and we have the vector format on the right there with our coefficient matrix. All right, in our initial conditions there, 1, 1, our coefficient matrix -4, -2 in the first row, because those are the coefficients of x and y in the first differential equation, and likewise for the second differential equation. Now, I'm not going through these steps in the video, but we can find the eigenvalues, and it turns out that for this particular system, one of them comes out to be 0, the other one comes out to be -5. And I'm labeling them lambda 1 and lambda 2 in that order. Now, we've got a pair of corresponding eigenvectors. So V1, this is the eigenvector associated to lambda 1, which for us is 0. This is the eigenvector associated to lambda 2, which is, in our case, -5. So we write down our general solution. It's a constant multiple of e to the lambda 1t times V1 plus K2 times e to the lambda 2t times V2. This time, though, again, e to the 0t, that factor is just 1. So we get K1 times our fixed eigenvector that we chose, V1, and then K2 e to the -5t times the other associated eigenvectors to that eigenvalue, which was 2, 1. All right, now enforcing those initial conditions, we'd be plugging in t equals 0, all right, and setting that equal to 1, 1 would give us that system of equations right there. Again, where does that come from? Our initial condition vector is 1, 1 when t is equal 0. So if we plug in t equals 0, the only place we can plug it in our formula for our general solution is the e to the negative 5t part. That's going to wipe that factor out, making it 1. That's going to lead us to that system of equations I have over on the left when we set the first components equal and the second components equal. Solving that system, you're going to get fractional answers. In this case, it's 1/5 for K1 and 3/5 for K2. So then we go up above and we're going to stick in here 1/5 for K1 and 3/5 for K2, and then just combine the vectors together. Okay, so we're putting in 1/5 and 3/5, multiplying the numbers or scalar functions into the components of the vectors, and then adding the first components and the second components. We see we have x of t here and y of t here are our component functions, and notice what they are linear combinations of. They're linear combinations of only e to the negative 5t in this case, and constants. This is the first time we're seeing constant terms as part of our answer. All right. So much the same, all right, is what we've done before. One just quick note I guess I'm going to make for this particular example. If you went through and you found the eigenvalue of 0, then looking at lambda equals 0, one of the corresponding equations we'd end up solving would be negative 4x minus 2y would equal 0, lambda times x. Well, 0 times x is just lambda, or pardon me, 0 times x is just 0. So solving this equation for, say, y, we would get negative 2y is equal 4x. Dividing both sides by negative 2, we would get y is equal negative 2x. All right, so very similar condition as we've seen before. In this example, I chose x to be negative 1. And if x is negative 1, then y is negative 2 times negative 1, which is positive 2, which is the eigenvector that I called v1 in this example. All right, so it's almost easier when lambda is 0 because the right-hand side gets wiped out. All right, now I've also got graphed, like in the previous videos, the direction field with the solution graphed on it. I have got two pictures here just to illustrate. The left picture is the graph with the solution to the initial value problem on it. Okay, so going back to that one, remember our initial condition was 1, 1, so we're at 1, 1 when t is equal 0, and in our case, as t goes to infinity, what's going to happen? We're going to go along this line and get closer and closer to that equilibrium solution at the end of that. Okay, looking back at our solution, let's just look at that for a minute. Once again, what's this going to approach as t goes to infinity? Well, the e to the negative 5t parts are going to wipe out. We're going to go to 0. We're going to approach negative 1/5, 2/5, the fixed vector. All right, as t goes to infinity. Let's just make sure that looks appropriate on the graph. Yep, seems about right. All right, thinking about your x value versus your y value. Yep, seems about negative 1/5 and 2/5 seems reasonable there. All right, the right picture is just kind of a picture of the phase portrait, where we have multiple solutions plotted on there, multiple equilibrium solutions. Also, notice the green dots; those are all equilibrium solutions. So the origin certainly is one, as it is for all of these homogeneous linear systems, but there's many others, right? And what we're seeing in this particular example is all of the solutions are going to approach one of the equilibrium solutions. Right? If you're not starting at an equilibrium solution, you're going to approach an equilibrium solution as t goes to infinity. The other possibility would be those arrows being reversed. If the eigenvalue was, say, positive 5 instead of negative 5, those arrows would be pointing away from the line of equilibrium solutions. And that's it for this video.